Hello, my name is Evan Chan, and this is my lab report for my Physics Lab 2. The introduction, we have the purpose of the lab. The purpose of the lab was to observe the motion of object free falling from rest, and to analyze the motion of the object using Newton's second law with 1, gravity only, and 2, with gravity and drag. And we wanted to compare these predicted positions of the object with the observed positions of the object with either just gravity or with both gravity and drag. And for the preview of the results, we want to have comparisons between the predicted positions graph and observed position graph to show that the observed positions graph was closer to the predicted positions graph that accounted for both gravity and drag. For the fundamental principles, physics principles we used in this lab were Newton's second law, or the momentum principle, in which we used these principles to observe the motion of the object in free fall. The formulas we use in the experiment are Newton's second law, F net equals dp over dt, gravitational force, Fg equals negative mg, drag force, Fd equals negative b, magnitude of v squared times v hat, velocity update formula, Vf equals Vi plus F net over m times delta t, and the position update formula, Rf equals Ri plus V average times delta t. We use these principles to observe free fall because we're able to use Newton's second law to find the position and velocity of the object. For the experimental data, I used this video right here on the right, just a paper ball falling. Using the video on the right and the tracker, I was able to come up with the data points you can also see on the right here. These data points will be later used to construct a graph for the position of the object and the velocity. The system here is the paper ball, and the surrounding is the earth and air. For the code of the gravity only position versus time graph and the velocity graph, the initial conditions here are that the initial position of the ball is 0, this number gotten from tracker, and the initial velocity of the ball is 0 since it starts from rest. I have the ball's mass equaling 0.0045 kg. The weight of the ball equals negative m. Negative ball.m times g times j hat is negative because the positive direction is up. And then we have the F net being equal to the weight of the ball. And then we have ball.vel equals the velocity update formula, which is ball.vel plus F net over ball.m times delta t. And we have ball.position equals the position update formula, which is just ball.position equals ball.position plus ball.velocity times delta t. For the code of the gravity plus drag, basically all the formulas above stay the same except for the b variable here, which was 0.0028, which was calculated by trying to get the predicted data as close to the observed data from tracker. And then we also have f drag, which was negative b times the magnitude of ball.velocity, second power times the velocity or the v hat. Then we have F net being equal to W plus F drag. Then everything else stay the same as well. For the predicted and observed position time graphs, in this graph, the blue data points represent the observed position versus time graph. The orange data points represent the gravity only predicted position versus time graph, and the red data points represent the drag and gravity position versus time graph. And as you can see, the gravity only predicted versus time graph tapers off towards the end of the data set, straying away from the observed data points. This confirms that forces other than gravity are acting upon the paper ball. And looking at the drag and gravity predicted position versus time graph, or the red data points, you can see that this is more closely resembling the observed position versus time graph, since this graph is accounting for both gravity and drag. The small deviation in the graph can be attributed to errors in putting the points in tracker for the video, or the drag constant being slightly off of the true value. However, the data points in the drag and gravity predicted observed position versus time graph are still very close to the data points in the predicted position versus time graph, and a lot closer than the gravity one. This shows that the experiment was relatively accurate in demonstrating Newton's second law, in which, since there was a force other than gravity acting upon the paper ball, the position of the ball couldn't be calculated with just the use of gravity, but we also have to account for the force of drag. For additional questions, what does it mean? By examining the graphs of the predicted models, we can tell that the model with drag predicted a terminal velocity, bottom right, as the graph looks to have an asymptote at negative 3.9 meters per second, while the gravity only predicted model just had a negative linear line for the velocity, which showed no indications of a terminal velocity. For the what if question, looking at the graphs, we can see that terminal velocity of both the object dropped from rest and the object thrown with the initial velocity will eventually have the same terminal velocity. However, the speed at which the objects reach their terminal velocities will be different, with the one thrown with the initial velocity reaching its terminal velocity a lot faster than the one dropped from rest. Conclusion: models using drag and gravity provide better predictions for the position of an object when compared to just using the gravity to predict the position. And terminal velocity is the same for the same object no matter what initial velocity it has, and the only thing that changes is how fast the object reaches terminal velocity. And that's it.